Hi, my name is Alex and I will be teaching you today about galvanic cells. So in this video, we will be looking at cell reactions and how the individual half reactions are occurring. We will set up a cell, we will be able to label important components of a cell, and discuss how these cells work. Before continuing on with this video, please make sure that you understand these three important concepts. 1. Be able to assign oxidative states to any compound. 2. Make sure you understand and know how to read an activity series. And 3. Be able to determine the reducing and oxidizing agent in any redox reaction. So in order to double check that you got this knowledge down, let's go ahead and do a self-test. So first, be able to assign the appropriate oxidative numbers to these three compounds. 2. Be able to know which iron can reduce, either aluminum or silver. And 3. Be able to assign the reducing agent and oxidizing agent in the below reaction. So go ahead, pause the video, and give it a try. So here are the answers to these problems that I had asked you to solve. Hopefully this was a really easy test for you and it was a good brain jog. But if not, make sure you refer to a general chemistry textbook and review what you had gotten wrong. To begin, let's discuss what a galvanic cell is. So a galvanic cell is a type of battery that can harness electric potential from redox reactions. And the cell works by separating out the oxidative reaction from the reducing reaction into separate containers. These containers are then connected together by a wire, which allows for the flow of electrons between the two half reactions. The reason these cells are so awesome is because they can be used to power things like a clock or a light bulb when they are connected in series to the cell. In this video, I am going to make what is called a Daniell cell. And this is a type of galvanic cell that uses zinc and copper. So to get started, I want to see if you can go ahead and assign the oxidative states to the above reaction. So go ahead and pause the video and give it a try. Hopefully you were able to get the same oxidative numbers that I had gotten. And what we see occurring in this reaction is that zinc is becoming oxidized and loses 2 electrons to copper. This means then that copper is then the atom being reduced. And we would actually expect this to occur based off the reactivity series because we know anything higher on the chart will reduce anything lower on this chart. And as you can see off of the reactivity series, zinc does indeed end up being higher than copper. So moving forward, let's go ahead and separate out our two reactions. Let's separate out the oxidative side, and we know that in the oxidative side, we know that zinc solid is forming zinc 2+, and it's losing 2 electrons in this process. Now for the reductive reaction, we know now that our copper 2+ ends up gaining 2 electrons from the zinc, and this ends up forming copper solid. So this actually ends up being our half reactions for the cell. And we can double check that these are our half reactions because they should add up to be the above reaction. And this is exactly what happens. If we add these up, we know that our electrons cancel because they're on opposite sides. And we know that our zinc solid and copper 2+ are on the same side. And our zinc 2+ and copper solid are also on the same side, and that's our products that are formed. And when comparing this reaction that we had just added to our above reaction, we see that they're the same. So now for the fun part, we can start to set up our very own cell. And the first thing we must do in setting up our cell is to separate out the two half reactions into their own container. So what I have set up here on the container on our left is I have a strip of zinc solid stuck into an aqueous zinc 2+ solution. And on the right hand side, I have copper solid stuck into a copper 2+ solution. Let's go ahead and add on another couple key components to our cell. What we have here in red is a wire, and this is just going to help in the flow of electrons between the two half reactions. Here in yellow, I have connected a voltmeter, and this is just going to tell us how large of an electric potential that we're getting out of the cell. And this U-shaped thing in gray is what's called a salt bridge. And a salt bridge is actually very important in keeping cell neutrality. And what happens is if we do not have a salt bridge, eventually we'll get charge buildup, and this will oppose the flow of electrons, making our cell no longer work. Now that we know all the important components of a cell, let's take a closer look at what's actually happening within this cell. So from earlier, we know that zinc solid is going to go ahead and form zinc 2 plus, and in order to do so, it's going to give up 2 electrons. And then over on the copper side, we know that copper 2 plus is going to react with 2 electrons, and it's going to form copper solid. Now, I want you to take a guess and see if you can get it right on which way electrons are flowing. Are they going to go ahead and flow to the right to copper, or are they going to go ahead and flow to the left to zinc? So take a second and see if you can think through this. So hopefully you made up your mind and you had said to the right to copper, which would make sense because zinc we know is giving up 2 electrons, and we know that copper needs 2 electrons. And the only way for this to happen is for those electrons to flow through the wire from the zinc side to the copper side. Now that we have determined the flow of electrons, let's take a closer look at what's occurring within the salt bridge. And so like I had said earlier, salt bridges actually become very important in keeping charge neutrality within the cell. Because what's actually happening over here on the zinc side is we're forming more of a positive charge, right? We're forming more zinc 2 plus. And so this means that the positive charge is going to increase on this side. Versus over on the copper side, we're actually using up copper 2 plus, and so our positive charge is decreasing on the copper side. So let's say our salt bridge is made out of potassium chloride. And potassium chloride is going to be able to separate out, and the potassium is going to go to one side and the chlorine is going to go to another in order to keep our original charge. So in this case, we know that the zinc side is becoming more positive, so therefore we need to increase the amount of negative charge that's going into it. So therefore, chlorine is going to flow over to the zinc side. And then over on the copper side, we know that we're decreasing the positive charge. So we need something that's going to replenish that positive charge. Therefore, potassium will flow over to the copper side. The next thing we can do is we can determine where our negative side and our positive side is on the cell. And the standard way to do this is to label the negative side as where your source of electrons is coming from. So in this case, this will be on the zinc side. And therefore then, the acceptor is going to be your positive side. Which makes sense because we're always told that electrons are going to flow from the negative to positive side, which is exactly what we see here. The last thing to do in our cell is to label the anode and the cathode. And we're going to do this by this simple sentence that states, the red cat ate an ox. Now the key components of this sentence are red cat and an ox. So what this tells us is that the reduced side is going to be the cathode and the oxidized side is going to be the anode. So go ahead, take a second and see if you can label correctly which side is going to be the cathode and which is going to be the anode. So hopefully you guessed correctly, and you said that the anode was on the zinc side and that the cathode was on the copper side, which makes sense because we know that zinc is becoming oxidized and that copper 2 plus is becoming reduced. Now here is an actual setup of the same cell that we have just created. And what I have done here in lab is that I put 3 of those cells side by side in series in order to give a little extra boost of power. Now, I know what you might be thinking. You might be asking yourself how my setup in lab is the exact same thing that we have just done in the PowerPoint. Well, don't get confused. The only thing that I have actually changed in the lab setup is that I've changed my salt bridge. And what you'll see is that central beaker in between my copper solution and zinc solution is a beaker full of salt. And from that beaker are 2 paper strips that are allowing the flow of salt from the central beaker out to the copper solution and the zinc solution. So when I go ahead and connect the cells to a voltmeter, I actually end up getting slightly over 4 volts, which ends up being quite a bit of power for these type of cells. And now for the real test. Let's hook up an LED bulb. And when I connect the LED and complete the circuit, the light does indeed light up. And now that is what I would call a success. Now that we have come to the end of the video, I would like to leave you with a fun at-home experiment to try on your own to see if you can better understand the material that we have just covered. So in this experiment, you will need different types of metals, different fruits, a potato, a voltmeter, and alligator clamps. And in this experiment, you are going to build a cell using the above material. And just as a hint, make sure you look at the picture in the upper right-hand corner to help you out. And when you're doing this experiment, I would like to see if you can answer these 3 questions. See if you can determine how a food cell works and be able to explain it. And just remember, it's just like a galvanic cell that we have just covered. And 2, see what type of metals work best and see if you can explain this using the activity series. And lastly, see what type of foods work best. And we didn't necessarily talk too much about this, but see if maybe you can come up with some ideas on why. So I would like to thank you again for watching my video, and I hope that you will be able to continue to use this material in your future studies.